Welcome to Real Physics and a video about the question, do we live in a black hole? Recently Sabin Hosenfelder brought this up, and I love her channel. She is courageous, she is to the point, but well, sometimes she needs to think a little bit more thoroughly. Let's dive into.
A group of researchers has published a paper claiming that we've got the Big Bang wrong. It was actually the collapse of an earlier universe to a black hole, which we now live in. That sounds wild.
No, that doesn't sound just wild, it's absolutely preposterous. You know what I don't like? That physicists, they kind of put together their ideas as if it was a menu they're pleased to have, but then they forget about their own theorems. I mean, there is the no-hair theorem saying that a black hole is described by mass, charge and angular momentum, and that's it. It means that from a scientific perspective, it makes absolutely no sense to postulate or imagine that there is structure in there, and certainly not an entire universe. And in addition, if our universe was a black hole, we would slowly evaporate, according to Hawking at least. Let's continue.
The thing is that on the inside, black holes can look very similar to our universe, so similar that we couldn't tell the difference.
Well, that we couldn't tell the difference is just a nice expression for that's not falsifiable and not science.
To understand why this isn't as nutty as it sounds,
well, it's still absolutely nutty, and the idea of a black hole isn't that complicated.
I need to make a brief excursion into how Einstein's theory of general relativity works.
And I dislike a little bit that attitude. No, I, the physicist, explaining you this very difficult Einstein's theory of general relativity. A smart Englishman, John Mitchell, already in 1783, just based on Newton's law, reasoned that, well, every celestial body has an escape velocity, and if it's very massive and very dense, that escape velocity may exceed the speed of light. So it doesn't take much of a genius to understand the concept of the black hole in the first place. And did Einstein predict that? Well, no. He said it was too much of an extrapolation of our known laws of nature, for a good reason. That being said, Einstein's general theory of relativity has been linked to black holes, and there was even a Nobel Prize for this for Roger Penrose in 2020. But if you read carefully, you see that he proved that a certain formulation of general relativity necessarily leads to the idea of a singularity. But that doesn't mean it is physical reality, okay? And with all respect for Roger Penrose, if you read this, he found out that there is something where all known laws of nature dissolve. I don't think this is a Nobel-worthy discovery, sorry. As a physicist, you're supposed to investigate where the known laws of physics work and show results and are confirmed, not where there are no valid laws of physics anymore. The other half of the 2020 Nobel Prize has been awarded to two researchers that showed that in the center of the Milky Way there is a very massive object of more than 4 million solar masses that has no visible counterpart. That's certainly a remarkable discovery, but it's also worth to keep in mind that this is not a quantitative proof of a black hole, because the size of a black hole, which is known as Schwarzschild radius, has not yet been measured. These are the facts. Now Sabin Hosenfelder goes on and tells a long story about all this has formed.
With common use, distribution analysis will not perfectly even, the same everywhere and in each direction, because physicists like silver things. Of course, like realistic, there is such thing as perfectly even distribution of propagating. When they make this, we expect this to be a problem.
But instead of going from the black hole of the galaxy to the universe, she explains why stellar black hole forms, which is okay, and it's related to the fact that indeed gravitational pressure of a star can overcome the pressure exerted by the quantum behavior of electrons inside. That was the discovery of Subrahmanyan Chandrasekhar, who was awarded the Nobel Prize in 1983. However, it doesn't really make sense to talk about this pressure, because this pressure strangely depends on the mass, and it is inversely proportional to the square of the mass. Think about that. Very strange. Here she correctly says that gravitational pressure exceeds the fermionic pressure, but that argument doesn't make any sense for the universe. And these considerations lead us to a serious problem, because if you look at this formula, the Schwarzschild radius, which is, you can imagine, as the size of a black hole, Strangely, it linearly depends on the mass, while any reasonable physical intuition would tell you that the mass depends on the third power, of course, of the size. So we would expect something like r to the third power, the volume of a sphere, being proportional to its mass. But it's not. So just to highlight this from another point of view, what are we doing here is a huge extrapolation of what we know. Because all the tests of general relativity work in the solar system, where this term, calculated with the mass of the sun, is very tiny with respect to about 1/1,000,000th. In other words, if you would make a black hole out of the sun, compressing it to the Schwarzschild radius, you would have to compress it from 700,000 kilometers to just 3 kilometers. So just to repeat, the quantitative thing we know about general relativity happens in our solar system at a stellar mass. If you go to 1,000,000 solar masses, you can observe something very interesting at the center of our galaxy. But then going to the entire universe means an extrapolation of 1 billion of billions. You go from 10 to the 41 kilograms to 10 to the something like 53. In other words, this is nonsense. By the way, also Sabin Hosenfelder says that
infinities aren't real either.
The thing Penrose got the Nobel Prize for doesn't exist. Now, to be fair, Sabin Hosenfelder expresses serious doubts about the validity of the result.
It's an ad hoc assumption.
But I see a pattern here in her videos, presenting new fancy stuff and then laying out in detail all the absurdities, and at the end she concludes, oh, this is nonsense.
It's half bullshit because I don't buy this stuff with the exclusion principle.
Yeah, well, you could say that earlier. But here is the best question of the video.
How does that work? Why is that so?
That question, why, is indeed, according to Schopenhauer, the mother of all sciences. And if you go a little bit deeper here, we see that a lot of absurdities coming out from these black hole calculations, something that should prompt you to think about the entire concept. I already said it's kind of absurd that the mass doesn't scale with the volume, but there is another more fundamental issue. All that belief in black holes hinges on the assumption that there is a gravitational constant 6.67 10 to the minus 11th valid in the entire universe. Why should that be the case? And that's a very deep question a lot of smart people have tried to answer, as I have outlined in a series of videos. One of them is Denis Shama in 1953, and he suspected that the gravitational constant has something to do with the mass distribution in the universe. That's not a God-given number, but something we potentially could calculate. He pointed out very convincingly that this fundamental issue hasn't been resolved neither by Newton nor by Einstein. By the way, such a calculation of the gravitational constant with the mass distribution of the universe would not only solve a lot of problems, such as the flatness problem, but ultimately explain why we tend to fool ourselves with the idea of the universe being a black hole. So whether you want to believe that particular approach of Shama or others, you should wonder about the question in general, if there are these constants of nature at all, or instead there is something we haven't understood yet. Because I think the idea that there is a God-given number invented by nature is just preposterous. I would call that the gods of modernity. Einstein, by the way, being in agreement here. And yes, this is the thing you should reflect upon. And my advice to Sabine, instead of following the latest fashions into every detail of absurdity, continue scratching your head, go to history and look up what the real reason for this fundamental problem could be. If you want to dive deeper into the matter, there are a couple of videos about Mach's principle, the gravitational constant, and how this is related to Einstein's first idea about general relativity in 1911. If you enjoyed the video, don't forget to like it, and if you're interested in fundamental physics, subscribe to this channel.